Hello everyone, and thank you once again for tuning in to my video on parametric equations and two-dimensional motion. This is the second of two videos, so if you haven't already viewed my first video, I ask that you please do that now before continuing to listen to this one here. In this video, we're going to pick up where we left off in that last video, where we were looking at the example where we had the position of a particle represented by the parametric equations of x equals cosine t and y equals sine t. And now, in part B, we're going to describe the motion of the particle at time equals pi over 4. Now, just like with one-dimensional motion, in two-dimensional motion, to describe where the particle is going, we can just examine the velocity of the particle. And in the prior video, we calculated the velocity vector as being negative sine t, comma cosine t. So, to particularly describe where the particle is moving at pi over 4, we need to examine the velocity vector at pi over 4. And so that would be negative sine of pi over 4, comma cosine of pi over 4. And that would be equal to negative square root 2 over 2, comma square root 2 over 2. And now that we have the velocity vector, we can describe exactly where the particle is moving. Because since the velocity vector has a negative x component, that means that the particle will be moving in a leftwards direction at time of pi over 4. And since the velocity vector has a positive y component, that would mean that the particle is moving upwards at time of pi over 4. Next, in our example, we're going to, in part C, find the magnitude of the velocity vector at time of pi over 4. If you recall, in the prior video, I talked about how we find the magnitude of any vector. And that was just essentially to take the square root of the sum of the squares of each of the components of your particular vector. Or in other words, just really calculate the distance on that particular vector. So, in this example here, we would basically need to do the same thing to our velocity vector at pi over 4. And we just did calculate the velocity vector at pi over 4. That was negative square root 2 over 2, comma, square root 2 over 2. And so with our velocity vector here, to calculate the magnitude, that would just be equal to the square root of the x component of the velocity vector, which is negative square root 2 over 2, and we need to square that. And then to that we will add the square of the y component of the velocity vector, which is square root of 2 over 2 squared. And so that would be our magnitude of our velocity vector at time of pi over 4. And just so that you're aware, instead of calling this the magnitude, instead you might be asked to find the speed of your particle, and basically that's the same thing as the magnitude of our velocity vector. And another way that we've expressed the speed, especially in one-dimensional motion, is to express it as the absolute value to our velocity. And this is going to play an important role in the next thing that we're going to actually calculate. Next in our problem, what we're going to do is, in part D, is to find the distance traveled by the particle from time of A to time of B. To do this, I'm going to recall upon things that we've already talked about, both in one-dimensional motion as well as in prior problems here. Recall that in one-dimensional motion, if I gave you the velocity of the particle, to find the distance traveled, you would have to perform some sort of integration on your velocity. But this particular depth interval here isn't always distance traveled. It'll always be the displacement of the particle, but not always distance. So to make sure that this will always equate to the distance traveled, if you recall, we have to take the absolute value to our velocity. Now, in two-dimensional motion, I claim that this particular formula that we just derived here for distance traveled will be exactly the same. So in two-dimensional motion, the distance will still be a definite integral from a to b of the absolute value of our velocity vector. But, as you recall in the prior problem, part C, the absolute value of the velocity vector is the same thing as our speed, which is also the same thing as our magnitude to our velocity vector. And that is calculated by taking the square root of the square of the x component to our vector, which for velocity, that's dx dt. So we have to square that. And then take the square of our y component of velocity. So the y component of velocity would be dy dt squared. So this here is your distance formula in two-dimensional motion with parametric equations. And if you're having a little bit of a deja vu here, you're not just dreaming things. This particular formula we already saw. We saw this on Tuesday, in particular when we calculated the length of a particular curve. And if you really think about it, hopefully this all makes sense, because if we're finding the distance traveled of our particular particle, which is traveling along a parametric curve, the two should really be the same. So in the example that we have here, the distance traveled by our particle from time of A to time of B should be a definite integral from A to B of the square root of the x component of velocity, which was negative sine t, and we have to square that, plus the y component of velocity, which is cosine t, and we'd have to square that. And this would be your distance traveled. Alright, so the last thing that you have to be able to do with two-dimensional motion is to find the position of a particle given its velocity vector. I'm going to go to a different example here to show you in particular what else might happen that you'll have to make sure you can do. In this example here, you see that the velocity vector is cosine t squared, comma, sine t cubed. You're also given the initial condition that at time of 0, the position is 4, 7. Now, you could be asked to find the entire position vector at a specific time, and you see here that was at time of 2. But for time's sake, we're just going to find the position of our particle at time of 2 for just the x component. I would hope that everyone here would agree that in order to do this, we would have to integrate our velocity vector to help find position. In particular, since we're just looking for the x component, that would mean that we would have to integrate cosine t squared. Now, with this type of problem, you would normally be allowed to use your TI-Nspire calculator. And if you had to integrate this, I would use your calculator, because if you do this on your calculator, the calculator is basically going to spit that out at you. And that's because, in this case here, there is no elementary antiderivative to this particular problem. So, in order to help still solve for the x position at time of 2, if you recall, what we do is, instead of just trying to integrate, we set up a definite integral. And the limits of integration for our integral we can get off of the problem. In particular, since we're given the x position at time of 0, that could be our lower limit integration, and since we're looking for position at time of 2, that could be our upper limit integration. And by the fundamental theorem of calculus, this particular definite integral should equate to the x-coordinate position at time of 2 minus the x-coordinate of position at time of 0. And so then, to finish this problem off, that particular definite integral there, your TI-Nspire calculator can get you an answer to. In particular, that would be 0.461461. And x of 0, we know that that is equal to 4. So to finish off the problem, x of 2 would just be equal to 4.461461. So that would give us our x component of position. If you also had to find the y component of position, you basically would do the exact same thing, just integrating the y component of velocity and using the y component of position at time of 0 to help you with finding the y coordinate at time of 2. So this concludes everything you need to know with parametric equations and in particular two-dimensional motion. If I don't see you tomorrow, please make sure that you look onto Moodle for the take-home assignment on parametric equations because it will be due when you come back from the break. I thank you for watching this particular video, and if I don't see you tomorrow, I hope everyone has a wonderful break. Take care.